Chapter 4, Section 3, Riemann sums and definite integrals. Well, we did types of Riemann sums. We did the lower sums and the upper sums in the previous section to approximate the area of the curve, and then of course we introduced how we could take the limit and let the number of subintervals get larger without bound, and then we could find the actual area. Well, now what we're going to do is we're not going to use always a regular partition. We're going to have, which of course means all the subintervals have the same length, which is the most convenient way to do it. But we can use subintervals that don't have to necessarily have the same width, and you will definitely see Riemann sums on the AP test. These sums are named after the mathematician George Friedrich Bernhard Riemann, who was known actually quite a bit for Riemann geometry. But there's another story in itself. I had to do a paper on him back in one of my education classes a million years ago in college. He lived in the 1800s. Didn't live to be very old, which is a shame that some of these mathematicians died so young. Galois, for example, I think was 21 or 22 when he died, because they were so brilliant. Who knows what kind of discoveries we would have and have earlier if some of these mathematicians that lived to be in their 60s, 70s, and 80s. But a Riemann sum says let f be defined on a closed interval from a to b, and now sometimes the symbol is written this way, which looks like a big triangle with an extra slash, and sometimes they put the extra slash this way. It kind of depends on the book. They'll have one or the other, so don't panic. I probably use it both ways, but I typically will put it on the right side and such. So this symbol actually represents the partition of the subinterval from a to b, such that if a is equal to x sub 0, which is less than x sub 1, less than x sub 2, less than x sub 3, all the way up to less than x sub n, which is b, then delta x sub I is the length of the ith subinterval. It's the right endpoint minus the left endpoint, and these don't always have to be the same. They can be. It can be a regular partition, but they don't have to be. And if we let c sub I be any point in the ith subinterval, as we have seen before, the limit as I go, or excuse me, the sum as I goes from 1 to n of f of c sub I delta x sub I, where c sub I is in the ith subinterval, is called a Riemann sum of your function f for that particular partition. Okay, you get a different partition, you get a different sum. Okay, different choices for c sub I, you get a different sum because it's a finite sum. We're not taking the limit of this. The width of the largest subinterval in the partition, which is this symbol, is called the norm of the partition, and we have like double absolute value bars around it. If you take the length of the subinterval b minus a and divide it by the largest of the subintervals, then this has to be less than or equal to n. And as the number of subintervals in the partition increases without bound, what that typically means is that the largest subinterval is going to go to 0, at least it does generally. So instead of the notation when we take a limit that we let n go to infinity, we're going to take the partition, the norm of the partition, and we're going to let that go to 0, because if the largest subinterval goes to 0, that means the number of subintervals is getting larger and larger and larger. Now, in this definition of Riemann sum, the function f has no restrictions. Doesn't have to be non-negative, other than it is defined on the interval from a to b. So on the AP exam, there are 3 different kinds of Riemann sums that we need to be able to find. We have what we call the left endpoint Riemann sum, the right endpoint Riemann sum, and the midpoint Riemann sum. So I'm going to try to show you examples of each one of these here. And here's the example that I have. Got the diagram drawn out for us here. So we have the function f of x equals 1/2 x squared plus 1 from 0 to 12, and we're going to have 4 subintervals, and the subintervals go from 0 to 2, so that has length 2, from 2 to 6, that has length 4, from 6 to 8, that has length 2, and from 8 to 12, that has length 4. This is not a regular partition, and I've kind of tried to draw it in there best that I could here. Here's the 2 and the 6 and the 8 and the 12 here. Of course, 0 here. Excuse me. 0 here. So we'll start with the left Riemann sum. Now, this function is increasing the way I've got this drawn out. You can see that. The left Riemann sum means that we're going to use the left endpoint, which would be a lower sum because this is an increasing function. But the left Riemann sum says that this rectangle that we're going to have in here is going to have height at the x value 0, so we're going to take f of 0 and we're going to take that times the width. So for the first one, the width is 2. Now for the next one, that's this guy here from 2 to 6, the left end point's the 2, so we're going to add to that f of 2 times the width, which is 4. And then for the next subinterval here, we're going to, from 6 to 8, we're going to look at the left end point, so we're going to have f of 6 for the height, and the width here of this subinterval is 2, and then one more. For this guy here, the left end point occurs at 8, from 8 to 12, so we're going to have f of 8 times the width, which is 8 from 12 is 4. So this is equal to f of 0, plug 0 in. Oh, plug 0 in. I'm sorry, I catch myself slanting the paper because of the way I write with my. I write at an angle here. F of 0 is 1 half times 0 squared plus 1 is 1 times 2. F of 2, so that'd be 2 squared, which is 4 times a half is 2 plus 1 is 3, so this would be 3 times 4. F of 6, 6 squared is 36, half of that's 18 plus 1 is 19 times 2. And then f of 8, that would be 64, half of that's 32 plus 1 is 33 times 4. So that would be 2 plus 12 plus, what did I get, 19 here? 19 times 2 is 38, plus 33 times 4 is 132. So that's what? That's 50. So that's 182, 184 square units there. That's for the left Riemann sum. Now for the right Riemann sum, it's very similar, except we use the right endpoint. So for the first subinterval from 0 to 2, we're going to use the y value here at x equal 2. So we'll have f of 2 times 2, the right endpoint, plus f of 6 times the width here is 4, plus for this guy here it'd be f of 8 times 2, and then for the last guy here it'd be f of 12 times 4. So this is going to be f of 2 is, well, I just did f of 2. F of 2 is 3, so this is 3 times 2. F of 6 was 19, so this is 19 times 4. F of 8 was 33, so this is 33 times 2. And f of 12 would be 144, 72 plus 1 is 73 times 4. So this is 6 plus 76, there's the spirit, plus 66, plus, let's see, 280, 292. So this would be 2, 8, 20, carry a 2. That'd be 31, 37, 37, 44. So I get 440 square units. Yikes, that's a significant difference in the left Riemann sum and the right Riemann sum. I'm hoping that the midpoint Riemann sum, and it should be based on this curve here being an increasing function, will have a value that will be closer to the actual area. It will be somewhere in the middle. Now with a midpoint Riemann sum, R sub m is the notation for that, the L for the left, the R for the right, and the M for the midpoint. We take the midpoint of each subinterval. So I've kind of drawn those in, like the midpoint of the first subinterval from 0 to 2 occurs at when x is 1. So it would look kind of like this. Part of it above, part of it below. And then here from 2 to 6 it'd be at 4, kind of look like this. And then between 6 and 8 it would be at 7, the midpoint, so it would kind of look like this. And then between 8 and 12 it'd be at 10, right? So it would kind of look like this. So we're going to find those at the midpoint. So this would be, for the first one, it'd be at 1. So f of 1 times 2 plus at the next one's at 4. F of 4 times 4. And then at 7, that'd be f of 7 times 2. And then at 12, it'd be or here at the last one, it'd be f of 10 times 4. F of 1 is, let's see, 1 1/2 or 3 halves. So this is 3 halves times 2. F of 4 would be 16, be 9 times 4. F of 7 7 would be 49 halves, 51 halves times 2, and then f of 10 would be 51 times 4. So this is what? 3 plus 36 plus 51 plus 204. So what would be 255, 285, 291, 294. I get 294, at least I hope I do here. And as it turns out, it is in between the two. Not dead center, but it is in between the two. And then typically it would make sense if you have an always increasing or always decreasing function that the midpoint Riemann sum would give you the best approximation. Now, from a sum, we apply a limit, and we're going to get what we call the definite integral coming up here. We're going to get the actual area under the curve. So we're going to define the definite integral in terms of that. It says if f is defined on a closed interval from a to b, and the limit as the norm of the partition goes to 0 of the sum as I goes from 1 to n of f of c sub I, remember that's somewhere in the ith subinterval, times delta x sub I, and we have to write it as delta x sub I because delta x's are not necessarily regular and all the same length. If this exists, then we say that the function f is integrable on the open interval from a to b, and that the limit is denoted, here's the limit again, limit as the norm of the partition goes to 0 of this sum is equal to, now notice what they have the integration symbol that we looked at in section 1 of this chapter, but then they have numbers that are at the bottom and at the top, and these are called the limits of integration. This is the lower limit of integration. This is the upper limit of integration of our function f of x dx. Now, you may wondered why back a ways that this particular symbol was used. Well, this is kind of an elongated s, and if you think about the elongated s, the s stands for the sum, which is how this thing was developed. So we use this symbol to essentially find the sum of all these infinitely many rectangles and add them all together to get the area under the curve. The limit is called the definite integral. The definite has these limits of integration of f from a to b. The number a is the lower limit of integration, and the number b is the upper limit of integration. Okay. Move this off to the side. Here's another theorem. We got lots of theorems. The existence of definite integrals. Now remember, continuity implies integrability, or I should say that the other way around. Differentiation implies continuity. Well, we kind of reverse the process. Continuity implies integrability. There's a good word to use for hangman sometimes. All continuous functions are integrable. If f is continuous on the closed interval from a to b, its definite integral from a to b exists. The definite integral yields a number. An indefinite integral, an antiderivative, gives us a family of functions because of the plus c. A definite integral is like the area under the curve. It's going to be a number. Since we have defined the definite integral as the limit of Riemann sum, it makes sense to think that the definite integral is the area under the curve, that the actual number here is going to give us the area under the curve. But of course, f must be continuous, and in case non-negative on AB. Now we're going to show you how to find area under the curve if it's not non-negative. There's a canceling effect if it's below the x-axis as compared to above the x-axis. Below the x-axis, the area is considered negative. So here's a theorem. The definite integral as the area of a region. If f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b, is given by this definite integral. Area equals the integral from a to b of f of x dx. So now we have two methods to evaluate a definite integral. We can use the limit definition that we showed at the end of the last section, and that we could apply easily to a Riemann sum, or we can use it as finding the area of the region. So if we have a nice enough region, maybe we can use our area formulas that we learned from our days in geometry or even pre-algebra to help us. Let's sketch and then evaluate using a geometric formula. So I have the definite integral from 1 to 5 of 2 dx. Well, from 1, 2, 3, 4, 5, from 1 to 5 of my function is y, or f of x equals 2. That's a horizontal line. That's a constant function. From 1 to to 5, well, I actually have a rectangle. This distance here is 4. This distance here is 2. So this is 4 times 2, which is 8. So the definite integral is actually 8. I use geometry to find the definite integral. And here's another one. Let's say g of x is this function, the square root of 9 minus x squared. Well, that's actually a semicircle. I'm never going to draw it as nicely as I should because I did not use a ruler to mark these out. I kind of freehanded them. But this is a semicircle with center at 0, 0 and radius 3. So the area under the curve I could find by 1/2 pi r squared, and r is 3. So this is 9/2 pi. So this definite integral from -3 to +3 is equal to 9/2 pi. So we can use geometry to evaluate a definite integral, which is way cool. Now, a couple of key ideas about definite integrals. Two special definite integrals says that if f is defined at x equal a, then the integral from a to a of f of x dx is equal to 0. Well, what happens is if the integral is going from a to a, think about it as a in terms of geometry. There is no region. The region has area 0, so it's equal to 0 because it's just a line segment. And if f is integral from a to b, then the integral from b to a of f of x dx, we're kind of reversing the limits of integration, is equal to the opposite of the integral from a to b of f of x dx. So if you flip-flop these two guys, you're getting the opposite of what you're going to start with. So look right here. In this example, if the integral from 1 to 4 of x dx is 15, then what is the integral from 4 to 1? Well, the integral from 4 to 1 of x dx, that's just interchanging the limits of integration. This is going to be -15. And here, the integral from 1 to 1 of any function that we're trying to integrate, this is equal to 0 based on these two special definite integrals. Now there's another one. Now remember, think of the definite integral as area under the curve. It says the additive interval property says if f is integrable on 3 closed intervals determined by a, b, and c, as I've got drawn here from a to b with c somewhere in the middle, and as it turns out, c doesn't even have to be in the middle. It can be out here, it can be out here, that the integral from a to b of f of x dx, that would be the area of the whole thing, is equal to the integral from a to c, that'd be this part of our function f of x dx, plus the integral from c to b, that'd be this part. And that makes sense because if you take these two parts and add them together, you should get the whole thing. Now this one says, what is the integral, the definite integral from -2 to 2 of the absolute value of x dx? I'm going to try to draw this out. So if I was to graph y equals the absolute value of x from -2 to 2, it would look like this. So what this is equal to is the integral from -2 to 2. Let's break it up from -2 to 0 of this guy right here, which would be what? Y equals the opposite of x, so this would be the opposite of x dx, plus the integral from 0 to 2 of x dx, because that's what y equals x this way. Now, we don't know how to evaluate this other than using geometry. This is a triangle, base 2, height 2, so this would be 1/2 times 2 times 2 plus 1/2 times 2 times 2. So this would be 2 plus 2, and it's still equal to 4, and that's what this definite integral is equal to. All right, using that 2 plus 2 again. Sorry about the angle. Every time I look at my screen, I can see that I've got it tilted there. Then the following theorems, some properties of definite integrals, and these are the linearity properties. If f and g are integrable on the closed interval from a to b and k is a constant, then the function k times f and f plus or minus g are integrable on a, b, and we get the following, that the definite integral from a to b of k times f of x dx is k times, you just bring the scalar out in front, it's got to be a constant, from a to b of f of x dx. And the integral of a sum is the sum or the integrals. The integral of a difference is the difference of the integrals. So we are still using the linearity properties. Very important. Now, if I know that the integral from 1 to 3 of x squared is dx, the integral from 1 to 3 of x squared dx is equal to 26 thirds, and the integral from 1 to 3 of x dx is equal to 4, and the integral from 1 to 3 of dx is equal to 2, I can evaluate, believe it or not, this integral. Because this integral from 1 to 3 of negative 2x squared plus 6x minus 5 can be broken apart into three integrals using these two properties. This is negative 2, the integral from 1 to 3 of x squared dx, plus 6 times the integral from 1 to 3 of x dx, minus 5 times the integral from 1 to 3 of dx. Brought the constant out in front, brought the constant out in front, and thought of this as bringing 5 times 1, brought the 5 out in front. So I have the 1 dx. This is given to be, where am I at? 26 thirds. So this is negative 2 times 26 thirds plus 6 times, that's 4, minus 5 times, and that, what did I get? 2 times 2. So this is negative 52 thirds plus 24, which is 72 thirds, minus 10, which is minus 30 thirds. So that's negative 10 over 3. And that's what that definite integral is equal to. Now I have one more theorem. Don't use it a ton, but it definitely makes sense. Hopefully it makes sense to you. This theorem is talking about what we call the preservation of inequality. If f is integrable and non-negative on a closed interval from a to b, then the integral from a to b of fx dx definitely has to be greater than or equal to 0, or 0 is less than or equal to it, because if it's non-negative, it's going to give us at worst, or at best, positive area under the curve. If f and g are integrable on a, b, and f of x is less than or equal to g of x for all x in the interval from a to b, then the integral from a to b of f of x dx is going to be less than or equal to the integral from a to b of g of x dx. That kind of makes sense. Here's y equals f of x, here's y equals g of x. This area is going to be more than this area. And that's what this is stating. All right? So take the time to really read through this and make sure you know how to do Riemann sums, because you're certainly going to see those again, not just in this textbook, but on the AP exam as well. Practice, practice, practice.